Okay, another video on the derivatives of sine and cosine. We got some examples that all use the chain rule. The first one is quite an interesting one. Y equals sine 4 theta in degrees, find dy d theta. So you can find the rate of angular change as well. The difference mainly is the degrees. Now basically derivatives of sine and cosine, using all the rules we're familiar with, work for radian measure. They're defined from first principles by radian measure. So we need to do some conversions, and you might remember that pi radians is equivalent to 180 degrees. So 1 degree is pi on 180 radians, and if we have 4 theta degrees, so we have 1 degree is pi on 180, 4 theta degrees is 4 theta times pi on 180, multiplying both sides by 4 theta degrees. So we would get then pi theta over 45 radians. So we need to substitute pi theta over 45 for 4 theta. So we make the substitution and we get to work. So we've got to find dy dx, or dy d theta I should say. Find the derivative, and we need to substitute here because we have a function of a function. So let u equal pi theta on 45. And remember, pi on 45 itself is just a real number, theta is the variable. So we basically need to go dy du d theta. So once we make the substitution, we have y equals sine of u. We also need to find the derivative du d theta. So du d theta, or the derivative of u with regard to theta, is pi on 45. And dy du, which is also required for the chain rule, is cos u. Putting it all together, chain rule, subbing it into the chain rule, in other words, we have dy du, which is cos u, times du d theta, which is pi on 45. Subbing it back in terms of theta, so unsubstituting back up here, so we have cos, let's put the constant on the front too, the pi on 45 on the front, cos pi theta over 45. Now we've just got one last thing to do, convert back in terms of how the question was given. It was given in degrees. So we're back in terms of theta, and now we've got to go back in terms of theta degrees. So we look back over to where we were. And that's a straight substitution back. Let's do that. Pi on 45 cos of 4 theta degrees. So let's compare the answer to the question. We had sine 4 theta degrees became pi on 45 cos 4 theta degrees. Okay, next example, we've got tan x now. We haven't dealt with tan x's yet, so here's tan x, and look, there is a rule, but like, I don't like learning lots of rules. I like to just understand how to get an answer. So understanding is important. There's two ways, well, there's two prominent ways of finding the derivative of tan x. So basically I'm going to focus on a method that uses the chain rule, but you could also use the quotient rule, which I'll start on the right, and remembering that the identity that tan x equals sine x over cosine x, we've got u over v, and so we can find dy dx by using the quotient rule. So just quickly, because we're focusing mainly on the chain rule in this video, but the quotient rule has been applied there. You can pause the video and have a close look. You'll notice now on the numerator here we have the other identity, the Pythagorean identity, so the numerator is 1. So it's 1 over cos squared x. So the derivative of tan x with respect to x is 1 over cos squared x. Let's see if we can get the same thing right now with the chain rule. We start by using the same identity, so tan x is sine x divided by cos x, and basically we can rearrange that into a product where we have cos x to the negative 1, and we do need to use I'm just using all the different notations in this video, okay, so we do need to, that's deliberate, like I'm just scattering them around. You wouldn't normally do that, but we've got all our notations for the derivative, okay. It's not all of them, but it's a lot of them. So we've got basically to use the, because this could be looked at as u times v, where v is an application of the chain rule, a nice simple one, and we've got uv dash plus vu dash for the product rule, and so we've got sine x. Now, time to calculate, or determine I should say, the value for v dash. So v dash is where we use the chain rule, so we can see here that, let's get some color happening, we've got an inner function cos x and an outer function something to the negative 1. So we've got to take the derivative of the outer function times the derivative of the inner function. So it's the derivative of the outer function is something to the negative 1, so it's negative cos x to the negative 2. You might need to step this out a bit more. And then the derivative of the inner function is negative sine x. So two negatives multiplied together make a positive, so we have sine x times cos x to the negative 2. Perhaps you'd like to arrange the expression like that, just applying index laws. So when we sub it back in for v dash over here, we've got sine x over cos x squared, or cos squared x. There was the other sine x there too, so we'll tidy that up on the next line. And we got cos x to the negative 1. So what we might do is be consistent here and put that on the bottom. So that's this cos x to the negative 1, because that's v. So we're going to put that on the bottom. And we've got u dash. U dash is simply the derivative of sine, which is cos. So we got sine squared x over cos squared x plus cos x over cos x, which is 1. Using the same denominators, we would have cos x over cos x would be cos x squared over cos x squared. So that means we would have sine squared x plus cos squared x all over cos squared x, using the same denominator. Again, the numerator is 1 and the denominator is cos squared x, and that's the same result as we got before. Yay!